Hello, welcome to the tutorial session for LUG 2022. We have 4 tutorials lined up for today. Thought I'd start by giving everyone a little bit of an overview about what the format will be like. Each tutorial has an hour slot allocated to it. The plan is the tutorials will probably go about 50 minutes or so, and we'll have about 10 minutes at the end for some Q&A time. Of course, everyone is welcome to ask questions during the tutorial. That's perfectly fine. We just wanted to have a little bit of time reserved at the end specifically for questions. But 10 minutes at the end too will also sort of serve as an informal break if anyone needs to step away for a minute before the next tutorial starts. As far as the sort of questions and answers, how they'll be handled, you should notice in your event portal that there is a little drop down to the right for live Q&A. If anyone has questions during the tutorial, please feel free to type in your question there. Myself and the presenters will be trying to monitor those questions and answer them live if possible, but all of them will be saved towards the end so we can loop back around to them. If for some reason we have more questions than we had time allocated, we can post answers to those questions after the fact, and they should still be accessible through the portal even after the tutorial is over. So I think that's all of the bookkeeping stuff out of the way. And so in about 10 minutes, we will be starting on the first tutorial presented by Anjus George from ORNL, titled Lustre MGC and Obdclass Deep Dive. So we will be joining everyone again in just a few minutes. Thanks. Okay, I'll go ahead and introduce our first tutorial today. Our first presenter will be Anjus George from Oak Ridge National Lab. Dr. Anjus George is an HPC system software engineer at the National Center for Computational Sciences at Oak Ridge National Laboratory. She primarily works on improving and enhancing the Lustre file system and developing system software for scientific edge ecosystems. Prior to joining ORNL, she earned her PhD from the University of North Carolina at Charlotte, where she designed and optimized distributed systems that enable machine vision at the IoT edge. Her research interests include distributed systems, operating systems, machine learning, and edge computing. She has also worked as a software product developer with Robert Bosch India, where she focused on developing engine management software for European automotive vehicles. And I will turn it over to Anjus George.
Thanks for the introduction, Rick. So let me share my screen. I hope you can see the screen.
Yes.
Okay. So hello, everyone. Today, I'll be presenting a tutorial on 2 subsystems from Lustre, MGC and Obdclass. So the outline of my presentation is as follows. I have divided the presentation into 2 sections. First section will cover the subsystem MGC. I will start with an introduction to MGC and describe about MGC Module Initialization and MGC Obd Operations. Then the detailed workflow of MGC setup and its operation is presented. I will conclude this section after talking about Lustre Log Handling along with other MGC operations such as MGC Cleanup, MGC Pre-Cleanup, and MGC Import Event. Section 2 starts with an introduction to Obdclass. I will move on to describe about Obd device structure and MGC Life Cycle and its various stages. Next topic covers different stages in Obd device life cycle, such as class attach, class export structure, and cleanup. I will conclude the tutorial by giving a short description on imports and export and some useful APIs in OBD class. So the Lustre client software involves primarily three components: a management client MGC, a metadata client MDC, and multiple object storage clients OSCs, one corresponding to each OST in the file system. Among this, the management client acts as an interface between Lustre Virtual File System layer and Lustre Management Server MGS. MGS stores and provides information about all Lustre file systems in a cluster. Lustre targets register with MGS to provide information to MGS, while Lustre clients contact MGS to retrieve information from it. The major functionalities of MGC are Lustre Log Handling, distributed log management, and file system setup. MGC is the first OBD device created in Lustre OBD device Life Cycle. So an OBD device in Lustre provides a level of abstraction on Lustre components such that generic operations can be applied without knowing the specific devices you are dealing with. So let's start from the MGC module initialization. When the MGC module initializes, it registers as an OBD device type with Lustre using the class register type function as shown in this source code here. So OBD device data and metadata operations are defined using OBD ops and MD ops structures. Since MGC deals with only metadata in Lustre, it has only OBD ops operations defined. The class register type function passes MGC OBD ops and Lustre MGC name as its argument. So Lustre MGC name is defined as MGC in the obd.h file. The MGC OBD operations are defined by MGC OBD op structure as shown here. The main operations that will be described here in the tutorial will be MGC setup, pre-cleanup, cleanup, import event, and MGC process config. So as you can see, all operations are defined as function pointers here. This type of programming style avoids complex switch cases and provides a level of abstraction on Lustre components to apply generic operations. So OBD ops structure can be used to share information between two subsystems in Lustre. So to understand how the communication between two subsystems work, let us take an example of MGC get info from the MGC OBD op structure. The subsystem LLite makes a call to MGC get info by passing a key as an argument, but note that the LLite invokes OBD get info instead of MGC get info. So OBD get info then invokes an OBP macro by passing an OBD export device and a get info operation. The definition of this macro then concatenates O with operation so that the resulting function call becomes MGC get info. So we know that we previously saw that O get info is defined as MGC get info in the MGC OBD op structure. So how does LLite make sure that this operation is directed specifically towards the MGC OBD device? So OBD get info from LLite has an argument called SBI LLMD export. The SBI structure is a type of LLSB info defined in LLite internal.h as shown in this figure. And the LLMD export field from LLSB info is a type of OBD export structure. The OBD export structure has a field export OBD, which is an OBD device structure. Another MGC OBD operation, OBD connect, retrieves the export using the OBD device structure. Now let's start with the first MGC OBD operation, MGC setup. So MGC setup is the initial routine that gets executed to start and set up the MGC OBD device. In Lustre, MGC is the first OBD device that is being set up as part of the OBD device lifecycle process. So to understand when MGC setup gets invoked in the OBD device lifecycle, let's explore the workflow from the Lustre module initialization. So Lustre module initialization begins from the Lustre init routine as shown in this figure. Lustre init invokes a register file system, which registers Lustre as the file system and adds it to the list of file systems for the kernel to be aware of. And Lustre FS type structure is defined in the source code. So here we can see the name of the file system is defined as Lustre, and the mount function is defined as Lustre mount. So when a user mounts Lustre, the Lustre mount function gets invoked. Lustre mount calls mount node function. Mount node invokes its callback function Lustre fill super. Lustre fill super is the entry point for the mount call from the Lustre client into Lustre. So Lustre fill super then invokes Lustre start MGC, which sets up the MGC OBD device to start processing startup logs. The Lustre start simple routine called here starts the MGC OBD device. Lustre start simple eventually leads to the invocation of OBD class specific routines, class setup, and class attach with the help of a do LCFG routine. So the do LCFG routine takes the OBD device name and a Lustre configuration command as arguments. Various Lustre configuration commands are LCFG attach, detach, setup, and cleanup as shown in this LCFG command type enum in the source code. Do LCFG takes the LCFG command LCFG setup and calls the class process config and passes the LCFG command that it received. In case of LCFG setup, the class setup routine gets invoked. Class setup primarily creates hashes and self-export and calls the OBD device specific setup. The device specific setup call is in turn invoked through another routine called OBD setup. So OBD setup calls the device specific routine with the help of the OBP macro as described before. So here in case of MGC OBD device, MGC setup defined as part of the MGC OBD op structure gets invoked by the OBD setup routine. So after MGC setup has been invoked, the operation of MGC setup is as follows. First, it adds a reference to the underlying portal RPC layer. Then it sets up an RPC client for the OBD device using client OBD setup. Next, MGC log init initializes Lustre logs, which will be processed by MGC at the MGS server. Next, MGC tunables init helps to initialize tunable parameters. Kthread run starts MGC requeue thread and it keeps reading the Lustre logs as the entries come in. Lustre extensively makes use of logging for recovery and distributed transaction commits. So the logs associated Lustre are called LL logs, and config logs, startup logs, change logs correspond to various type of LL logs. The LLog reader utility can be used to read these Lustre logs. So when a Lustre target registers with MGS, the MGS constructs a log for the target. Similarly, a Lustre client log is created for the Lustre client when it is mounted. When a user mounts the Lustre client, it triggers to download the Lustre config logs on the client. MGC subsystem is responsible for reading and processing the logs and sending them to Lustre clients and Lustre servers. So Next, we'll move on to the log processing in MGC. So Lustre fill super function that is described before makes a call to LL fill super, which initializes a config log instance specific to the super block passed from Lustre fill super. Since the same MGC may be used to follow multiple config logs, the config log instance is used to keep the state for a specific log. Afterwards, Lustre fill super invokes Lustre process log, which gets a config log from MGS and starts processing it. So the Lustre process log gets called for both Lustre clients and servers, and it continues to process new statements appended to the logs. The Lustre process log first resets and allocates Lustre configuration buffers and calls the OBD process config function. The LCFG command passed to MGC process config is LCFG log start, which gets the config log from MGC, start processing it, and adds the log to the list of logs to follow. So config log add function is the function that adds the log to the list of active logs watched for updates by MGC. And a few other important log processing functions to be considered here in MGC are MGC process log that gets a configuration log from the MGS and processes it. Next one is MGC process recover node map log. This is called if the Lustre client was notified for target restarting by the MGS. So next, we will look at the MGC pre-cleanup and MGC cleanup functions. So cleanup functions are important in Lustre in case of file system unmounting or any unexpected errors during the file system setup. The class cleanup routine starts the process of shutting down an OBD device. This involves MGC pre-cleanup, which makes sure that all the exports are destroyed before shutting down the OBD device. MGC pre-cleanup first decrements the MGC count, that was incremented during the MGC setup. So MGC count keeps track of the count of the running MGC threads and makes sure not to shut down any threads prematurely. Next, it waits for any requeue thread to get completed and calls the OBD client import function. So the OBD cleanup client import destroys a client-side import interface of the OBD device. Finally, MGC pre-cleanup invokes the MGC LLog fini function, which cleans up the Lustre logs associated with the MGC. And the log cleaning is accomplished by the function LLog cleanup. So MGC cleanup function then deletes the profiles for the last MGC OBD device using class delete profiles. When MGC sends a buffer of data to MGC, when MGS sends a buffer of data to MGC, the Lustre profiles help to identify the intended recipients of the data. Next, the LProcFS OBD cleanup routine removes sysfs and debugfs entries for the OBD device. So it then decrements the reference to the portal RPC layer and finally calls client OBD cleanup. So this function makes the OBD namespace point to null and destroys the client-side import interface, and finally frees up the OBD device using OBD free macro. So this figure shows the workflows for both MGC setup and MGC cleanup routines in MGC parallelly. So after the OBD pre-cleanup, UUID export and NID export hash tables are freed up and destroyed. So UUID export hash table stores UUIDs for different OBD devices, whereas NID export hash table stores the portal RPC network connection information. So the next MGC Obd operation that we will look at is the MGC import event. So MGC import event function handles the event reported at the MGC import interface. The type of import events identified by MGC are listed in this OBD import event enum in this source code. So client-side imports are used by the clients to communicate with the exports on the server. For example, if MDS wants to communicate with MGS, MDS will be using its client import to communicate with MGS's server-side export. So imports and exports will be explained in detail in one of the sections, one of the parts from the OBD class section in this tutorial. So that concludes the section 1 of the tutorial, and section 2 starts with an introduction to OBD class. The OBD class subsystem in Lustre provides an abstraction layer that allows generic operations to be applied on Lustre components without having the knowledge of specific components. The MGC, MDC, OSC, LOV, and LMV are examples of OBD devices in Lustre that makes use of the OBD class generic abstraction layer. The OBD devices can be connected in different ways to form client-server pairs for internal communication and data exchange in Lustre. So the client and server referred here are service clients and server roles temporarily assumed by the OBD devices, but not physical nodes representing Lustre clients and Lustre servers. So OBD devices in Lustre are stored internally in OBD devs array as shown in this source code. The maximum number of OBD devices in Lustre per node is limited by the max OBD devices as shown here. So OBD devices in the OBD devs array are indexed using an OBD minor number. An OBD device can be identified using its minor number name or UUID. UUID is a unique identifier that Lustre assigns for OBD devices. And the LCTLDL utility can be used to view all the local OBD devices and their UUIDs on Lustre clients and Lustre servers. See, so the structure that defines an OBD device is the OBD device structure, which is shown in this source code. So the first field in this structure is OBD type that defines the type of the OBD device, a metadata or a bulk data device or both. And OBD magic is used to identify data corruption with an OBD device. So Lustre assigns a magic number to the OBD device during its creation phase and then later asserts it in different parts of the source code to make sure that it returns the same magic number to ensure data integrity. So OBD minor is the index of the OBD device in the OBD devs array, and an LU device type is applicable only for the OBD only for a real device such as an LDiskFS or CFS type of block device. OBD UUID and OBD name fields are used for UUID and name of the OBD device as the field name suggests. OBD device structure also includes various flags to indicate the current status of the OBD device. So some of those are OBD attached, which means it has completed the attach, and then OBD setup indicating the device setup has finished. Then OBD stopping indicates it has started the cleanup process, and OBD starting indicates that it has started the setup process of the OBD device. So OBD UUID hash and OBD NID hash are the UUID export and NID export hash tables for the OBD device. An OBD device is also associated with several linked lists pointing to OBD NID stats, OBD exports, OBD unlinked exports, and OBD delayed exports. Some of the remaining relevant fields of this structure are OBD exports, K object device model abstractions, timeouts for recovery, proc entries, directory entry, and so on. So now let's start with the life cycle process of the MGC OBD device. So MGC is the first OBD device set up and started by Lustre in the OBD life cycle, as mentioned before. To understand the life cycle of MGC OBD device, let's start from the generic file system mount function, VFS mount. So VFS mount is directly invoked by the mount system call from the user. It handles the generic portion of the mounting of the file system. It then invokes file system specific mount function Lustre mount. The Lustre mount invokes kernel function mount nodev, which is shown in the source code here. The mount nodev then invokes Lustre fill super as its callback function. So Lustre fill super is the entry point for mount call into the Lustre. This function initializes the super block, Lustre super block, which is used by the MGC to write a local copy of the config log. The Lustre fill super routine calls LL fill super, which initializes config log instance specific for the super block. The config log instance structure is shown in the source code here. So the config instance field in the structure is unique to the super block, and this unique config instance field is obtained using LL get config instance function defined in obdclass.h. The config log instance structure also has a UUID and a callback handler defined by the function class config LL log handler. The file system name field of LLSB infrastructure is populated by copying the profile name obtained using the get profile name function, and this obtains a profile name corresponding to the mount command issued from the user from the Lustre mount data structure. So we have explained until here. So the LL fill super then invokes the Lustre process log function, which gets the config logs from MGS and starts processing them. This function is called from both Lustre clients and servers, and it will continue to process new statements appended to the logs. The three parameters passed to the function are super block, log name, and the config log instance shown in the previous slide. The config log instance is unique to the super block and which is used by the MGC to write a local copy of the config log. Log name is the name of the LL log to be replicated from the MGS. The config log instance is used to keep the state for a specific config log. It can be from OST1, OST2, and any Lustre client. The log is then added to the MGC's list of logs to follow. So Lustre process log then calls OBD process config that uses the OBP macro to call MGC specific MGC process config function. MGC process config gets the config log from the MGS and processes it to start any services. And logs are also added to the list of logs to watch. So MGC process config invokes several subfunctions. The config log add function categorizes the data in config log based on if the data is related to portal RPC layer configuration parameters and node maps or barriers. The log data related to each of these categories is then copied to memory using the function config log find or add. So MGC process config then next calls the MGC process log function, and it gets the config log from MGS and processes it. This function is called for both Lustre clients and Lustre servers to process the configuration log from the MGS. The MGC process log then calls MGC process config log function, which reads the log and creates a local copy of the log on the Lustre client or server. This function first initializes an environment and a context using the LU environment init and LLog get context functions. The MGC LLog local copy routine is used to create a local copy of the log with the environment and context previously initialized. So real-time changes in the config log in the log are parsed using class config parse LLog function. The arguments passed to class config parse LLog function are the environment, context, and config log instance initialized in MGC process config log function and the config log name. So the first log that is being parsed by the class config parse LLog function is start log. Start log contains the configuration information for various Lustre file system components, OBD devices, and file system mounting process. So class config parse LLog first acquires a lock on the log to be parsed using a handler function, LLog init handle. It then continues the processing of the log from where it has last stopped till the end of the log. So to process the logs by the class config parse LLog function, two entities are required. First one is an index to parse through the data in the log, and second one is a callback function that processes and interprets the data. The callback function can be a generic handler function like class config LLog handler, or it can be customized as well. Additionally, the callback function provides a config marker functionality that allows to inject special flags or for selective processing of data in the log. The callback handler also initializes Lustre configuration buffers to temporarily store the log data. Afterwards, the following actions takes place. So it translates the log names to OBD device names. It appends UUID with OBD device name for each Lustre client mount, and it finally attaches the OBD device. So each OBD device then sets up a key to communicate with other devices through secure portal RPC layer. The rules for creating this key are stored in the config log. OBD device then creates a connection for communication, and start log contains all the state information for all configuration related to devices. The Lustre configuration buffer stores this information temporarily, and OBD device use this buffer to consume log data. After creating a connection, the handler extracts information such as UUID, NID required to form the configuration logs. So the LL log record header decides what type of information should be parsed from the logs. For instance, OBD CFG record indicates the handler to scan the OBD devices, device configuration information, and change log record asks to parse the change log records. So using NID and UUID information about the OBD device, the handler now invokes class process config routine. This function repeats the cycle of OBD device creation for other OBD devices. And notice that we have only MGC as the OBD device in the OBD device lifecycle right now. So this function repeats the cycle and creates other OBD devices. The class process config function calls the generic OBD class functions such as class attach, class setup, depending upon the LCFG command it receives for a specific OBD device. So moving on to the first lifecycle function class attach. So class attach first registers and adds the OBD device to the list of OBD devices, which is defined by the OBD devs array. As mentioned before, the attach function first checks if the OBD device type passed is valid or not. The OBD type structure is defined as shown in the source code. Two types of operations defined in this structure are OBD ops, data operations, and MD ops, that is metadata operations. These operations determine if the OBD device is destined to perform data or metadata operations or both. So the LU device type field of OBD type structure is applicable only for real block devices such as CFS and LDiskFS OST devices. So the LU device type differentiates metadata and data devices using the tags LU device DT and LU device MD. So an example of an LU device type structure defined for an LDiskFS OST type is shown here. So we will now go through the detailed workflow of class attach function. This figure shows the complete workflow of the class attach function. The class attach first calls class newDev function. The class newDev function then invokes class getType function. So class newDev creates, allocates, and initializes a new OBD device. And class getType registers an already created OBD device and loads the OBD device module. The OBD device then creates a self-export using the function class new export self. A self-export is created only for a client OBD device. The last part of class attach is registering or listing the OBD device in the OBD devs array, which is done through class register device function. So this function assigns a minor number to the OBD device that can be used to look up the OBD device in the OBD devs array. So the OBD's export structure represents a target side export connection for OBD devices in Lustre. So for every connected client, there exists an export structure on the server attached to the same OBD device. So some of the important fields of the structure are export handle. So on connection establishment, the export handle ID is provided to the client, and the subsequent client RPCs contain this handle ID to identify which export they are talking to. So this structure also contains some counters to keep track of references. So for example, export RPC count keeps track of the number of RPC references. Export CB count counts the commit callback references, and export logs list maintains a linked list of all the logs, and export client UUID is the UUID of client connected to this export. And finally, the export OBD chain links all the exports on an OBD device. So the next function that we will discuss in the OBD device lifecycle is class setup. So class setup, the primary duties of class setup is to create hash tables and self exports. And then it calls the OBD type specific setup function. So as an initial step, this function obtains the OBD device from the OBD devs array using OBD minor number. Then it sets the OBD starting flag to indicate that the setup of this OBD device has started. So a generic device setup function OBD setup is then invoked by class setup by passing the OBD device structure populated and the corresponding LCFG command LCFG setup. So OBD setup then invokes the device specific setup functions such as MGC setup, LWP setup, etc. So all of these setup routines invoke a client OBD setup routine that acts as a pre-setup stage before the creation of imports for the clients. So client OBD setup populates the client OBD structure. So client OBD structure is used for page cache and extended attributes management. It comprises of fields pointing to OBD device, UUID, and import interfaces, consists of several counters to keep track of client connections and fields to represent maximum and default extended attribute sizes. Few other fields used for cache handling are CL cache, which is the LRU cache for caching OSC pages, CL LRU left that maintains the LRU slots per OSC cache, and CL LRU busy indicates the number of busy LRU pages, and CL LRU in list keeps track of the number of LRU pages in cache for this client OBD. So, the client OBD setup then obtains an LDLM log to set up the LDLM layer references for this client OBD device. It then sets up a port LRPC request and replay using port LRPC init client function. The client OBD structure defines a pointer to the OBD import structure. The OBD import structure represents port LRPC imports that are client-side view of the remote targets. A new import connection for the OBD device is created using the function class new import by populating this structure. A new the new import connection that is created using the client OBD setup adds an initial connection for the OBD device to the port LRPC layer by invoking client import add connection method. So finally, client OBD setup creates a new LDLM namespace for the OBD device that it just set up using the LDLM namespace new routine. This completes the setup phase in the OBD device lifecycle, and the newly set up OBD device can now be used for communications between subsystems in Lustre. So we will now move on to the class pre-cleanup and class cleanup lifecycle functions. So the Lustre unmount process begins from the LL unmount begin function defined as part of the Lustre super operation structure. The LL mount begin function accepts a super block from which the metadata and data exports for the OBD device are extracted using the class export to OBD routine. The OBD force flag from OBD device structure is set to indicate the cleanup will be performed even though the OBD reference count is greater than 0 currently. Then it periodically checks and waits to finish until there are no outstanding requests from the VFS layer. The cleanup cycle then invokes LL put super routine. So this function obtains config instance and profile name corresponding to the super block using LL get config instance function and get profile name functions. Next, it invokes the Lustre end log function by passing the super block profile name and config log instance initialized here. The Lustre end log function ensures to stop following updates for the config log corresponding to the config log instance passed. Lustre end log resets the Lustre configuration buffers and calls the OBD process config by passing the LCFG command, LCFG log end, and MGC as the OBD device. So this results in the invocation of MGC process config, which calls the config log end method when LCFG log end is passed. The config log end finds the config log and stops watching for the updates for the log. After that, the LL put super invokes class devices in group function, which iterates through the OBD devices with the same group UUID and sets the OBD force flag for all devices. Afterwards, it calls the class manual cleanup routine, which invokes OBD class functions, class cleanup, and class detach in the order. So the class cleanup is invoked through class process config, bypassing the LCFG cleanup command. The class cleanup starts the shutdown of the OBD device. It sets the OBD stopping flag to indicate that cleanup has started. Then it disconnects all the exports using class disconnect exports function, and that ensures that all exports are destroyed. The OBD pre-cleanup calls device-specific cleanup routine, such as MGC pre-cleanup, and class cleanup then destroys the UUID export, NID export, and NID stats hash tables and invokes class decrypt function. So this just asserts that all exports are destroyed again, and then class manual cleanup then invokes class detach function bypassing the LCFG detach command. Class detach makes sure that the OBD attached flag is 0, and it unregisters the device. So it basically frees the slot in the OBD devs array using class unregister device function. Next, it invokes the class decrypt function that destroys the last export by calling the class unlink export method. So class unlink export calls the class export put that frees the OBD device using class freedev function. Class freedev calls device specific cleanup through OBD cleanup, and finally invokes class put type routine that unloads the module. So this is the end of the life cycle for the OBD device. Next, I want to cover an important topic, which is imports and exports. So Lustre components such as MDT and OST need one client device to establish communication between them. So this is also applicable in case of Lustre client communicating with Lustre servers. So client-side OBD devices consist of self-export and import, whereas server-side OBD devices consist of exports and reverse imports. A client OBD device then sends requests to the server using its import, and the server receives requests using its export, as illustrated in this figure. So the imports on server OBD devices are called reverse imports because they are used to send requests to the client OBD devices. These requests are mostly callback requests sent by the server to clients infrequently, and the client uses its self-export to receive these callback requests from the server. So for any two OBD devices to communicate with each other, they need an import-export pair. For instance, let us consider the case of communication between OST and MDT OBD devices. So logging into an OSS node and doing the command lctldl shows the OBD devices on the node and associated details such as OBD device status, type, name, UUID, etc. Now, examining the sysfs Lustre directory can also show the OBD devices corresponding to various device type. So, for instance, the name of an OBD device created for data exchange between OST5 and MDT2 will be like MDT2 LWP OST5. This means that the client OBD device that enables the communication here is LWP. So a conceptual view of the communication between OST and MDT through OSP OSP OBD device is also shown in the figure. LWP OBD device manages connections established from OST to MDT and MDTs to MDT0. So an LWP device is used for used in Lustre to send quota and FLD query request. This figure also shows the reverse communication between MDT and OST through OSP client OBD device. So the OBD filter directory from procfs Lustre lists OSTs present on the OSS node. All of these OSTs have their export connections listed in the NID format in their respective exports directory. So export connection information is stored in a file called export in each of the export connections directory. Viewing the export file for corresponding to MDT2 shows the following fields. Name, this shows the name of the OST device. Client, the NID of the client export connection. Connect flags, which will be the flags representing various configurations for LNet and portal RPC connections between the OBD devices, and a few other fields such as connect data, export flags, and grant, etc. So I would like to conclude this tutorial by pointing out a few useful APIs in the OBD class. So all OBD class related function declarations are listed in the obd class.h file, and their definitions can be seen in genops.c file. So some of the important and useful APIs in OBD class are class new dev. This creates an OBD device, allocates and initializes it, and class free dev. This will be freeing an OBD device, and class register, unregister and register device unregisters and registers the OBD device, and class name to dev function returns minor number corresponding to an OBD device name. Class name to OBD, this will return a pointer to an OBD device structure corresponding to the device name. Class UUID to dev returns minor number of an OBD device when the UUID is provided. And there are a few other more useful APIs in OBD class. So I would like to encourage you all to please go and see the other useful APIs and other subsystems discussed in Lustre in this Understanding Lustre Internals wiki page created by us. So I have tried to cover the important topics in MGC and Obd class subsystems, but a few more deep dive topics can be found in this page, Understanding Lustre Internals, which is hosted in the wiki.lustre.org website. And with that, I would like to conclude this tutorial. So before I go, I would like to thank Lustre team from ORNL. So that will include James Simmons. So thank you for taking time to explain the source code of Lustre and patiently answering all my questions related to the source code. And thanks for Rick Moore to contribute towards the documentation and also actively participating in all our code exploration discussion. And last but not least, thanks to Sar Poral from ORNL for providing me the resources to conduct the Lustre code source code exploration, and also encouraging me to pursue this documentation. So thank you all for your time and attention. If you have any questions, I'm open to answer the questions now.
Thank you, Anjus. Don't seem to have any questions coming in. Oh, one just came in. Andre Stilgrass, are you going to be adding comments to the code based on this document?
Yes, definitely. So that is one of the future enhancement. that we are considering. So based on our code exploration and studies on the Lustre subsystems, we will definitely add the documentation inside Lustre source code as well. So thanks for pointing that out.
We also had a question from Sebastian asking if we could please share the full link to the wiki page.
Yes,
and
definitely.
it looks like someone may have beat us to the punch.
Oh, okay. Yeah, that's the one. That's right. So I can reply. I can answer.
We'll post that. We'll post the full link in the answer too. That way it'll be there for to see it.
I just answered. I just answered with the full link, and I'm not sure if it came through.
I believe it did. Yes.
Oh, okay, it came through. Okay, thanks.
For anybody who's following the questions, when a question's been answered, there's a special answered questions tab, and the question will move over there if you need to go back later and refer to those answers. Are there any other questions? If not, then we will begin the next tutorial in about 5 minutes. Thank you.